All right, so we start with the basic first moment. So what is first moment? The first moment is the expectation of a random variable. So let's see a very, very basic but useful fact. So, first moment method. Okay, so we have the first moment in the easy sense. Let's start with something that's almost trivial. So if you have some numbers, so if we have, let's say, if you have x1, let me use. If you have natural numbers, a1, a2, dot, 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 to an, this is like natural numbers or integers. And their average is, let's say, a. Then what do we know? We know that there must exist one of this number that's at most this average, right? There exists some ai that's at most a, and some aj that's at least a. Okay, this is almost trivial. And the first moment, one part of the first moment is the probabilistic version of this. We have a random variable, and the average is replaced by its expectation. Then we know that there exists, with positive probability, this random variable will take value at least its expectation, or the other way around. This is the first thing we will see, proposition. So probabilistic version. So x is a random variable. Okay, then we have the probability that x is at least its expectation must be positive, with positive probability be at least, and also the other way around. X is at most its expectation is positive. Okay. For completeness, let's prove this theorem. So let's prove by contradiction. By symmetry, let's just prove this one. Suppose x almost never takes value at least its expectation. X at least ex is 0. We're going to derive a contradiction. So if this is its expectation, and we suppose x never takes value at least ex, that means x is somewhere here, right? Let's partition it into parts. Let's partition it. This is ex minus 1/2, dot, dot, dot. We let, for natural number n, we let en be the event that x takes value between, the en be the event that x is at least, or strictly bigger than its expectation minus 1 over n minus 1, less than equal to its expectation minus 1 over n. Okay, this is the event. For convention, we're going to write one where expectation minus 1 over 0 is negative infinity. Okay, 1 over 0 is infinity. Good. So we know the union of this event this is always to the left of the expectation. So the union of these events sum up to probability 1. So we have, by definition, sum over all n, at least 1. Wait. Something is strange. There's a typo here, right? This seems to be larger than this. Wait a second. If the denominator is smaller, this gets smaller, the whole numeration, the whole thing gets larger, minus a larger number gets smaller. And that's correct. So if I let n equal to 1, wait a second, if I let n equal to 1, this is expectation minus 1, x bigger than expectation minus 1 over 0, negative infinity. Okay, yeah, this is this part. Expectation minus 1 to negative infinity, okay? And then expectation minus 1 to expectation minus 1/2, expectation 1/2 to 1/3, so on and so forth. Okay, no problem. So when n is at least 1, the sum of all these events sum up to 1. This is everything. We then have, let's write out what's this expectation. Expectation of x, let's upper bound it. This is at most, for every x, it's less than this. Okay, so we have, this is at most, sum over n at least 1. For every x, it's less than ex minus 1 over n times the probability that en happens. So under this event, x is less than that. This happens for all n this holds. Okay. Then this is equals to, let's expand it. This is constant. Sum of this is 1. So just get out to just sum of the expectation of x minus sum of 1 over n at least 1 expectation probability of en. And now we get a contradiction because the sum of this is 1. One of this term of the probability must be positive. If everything is 0, the sum of probability will be 0, right? So one of this is positive, multiplied by some factor that's positive. You subtract something that's strictly positive, so less than expectation of x. We get a contradiction. As there must exist some n with probability of en to be positive. Any question? Okay. Now let's see some application of this seemingly trivial fact that for a random variable with positive probability, x is at least its expectation, or the other way around. So the first application is about set systems. Suppose now we have a collection of sets. Okay, applications. So first thing is, suppose we have a collection of set systems, uniform. You have, the setup is you have A1, AN, which half sets in ground set of size n. Okay. Now we suppose their intersection is not too large. Suppose a pairwise intersection is not too large. In other words, their Hamming distance is lower bounded by some distance. They are not so close. It's pairwise far apart. So you can think of this as pairwise far apart. Okay. Condition. For every I and j. Now the question is, how large can n be? How many such sets, half sets, we can have so that they are pairwise far apart? The first application of first moment is we will see that we can take exponential in little n many sets that are pairwise far apart in this sense when alpha is strictly bigger than 1/4. Okay. And why 1/4 is important? Let's first get some intuition. If we choose, so the answer there's a transition, there's a change of behavior at alpha equal to 1/4. So why this number? Intuition. If we choose randomly half sets, so for random, here's intuition. For random half sets, the expected size of their intersection is what? Each one is 1/4, right? So you can think of one half set as with probability 1/2, you pick an element to put it into set A. You have two half sets. Now, to lie in A union B is like you need to be probability 1/2 to be picked by A and probability 1/2 to be picked by B independently. So that's 1/2 multiplied by 1/2. The expected size is n/4. So most likely when you typically pick two half sets, their intersection is around n/4. Therefore, it makes sense that when alpha is strictly bigger than n/4, we can pick many such sets. Okay, so the intuition is so when alpha bigger than 1/4 can have many such well-separated sets. Whereas when alpha strictly less than 1/4, we can only pick very few. We can only have few. These parts, we will only see this part. That's the first moment. The second part, it relates to dimension argument. We've covered it, I believe, last semester. Actually, when alpha strictly less than 1/4, you can only have constantly many such sets that are well separated. So let's see this one here. This is the theorem. When the theorem is when alpha is bigger than 1/4, we can pick exponential in little n many sets that are pairwise intersection sizes and most of this alpha n. And how we're going to pick it? We're just going to pick it randomly. Okay. And by this intuition, most of them, we can pick many of them so that pairwise their intersection is strictly less than alpha n. So let's first estimate a random set. Let's fix here's the proof. Let's first estimate two random sets, the probability that their intersection is strictly bigger than alpha n. And let's first estimate the probability that two random n/2 sets have intersection larger than alpha n. Just by how do you say translation, you can uniform random set, you can assume one set is fixed, and you take the another random set. So this is the same. So we fix the first random set to be the elements 1 to n². So two random sets. So let's let A be a uniform random set of size n/2 and estimate the probability, that A intersect the other half sets, that's the first n², the size intersection to be strictly bigger than alpha n. Right? This probability equals to, let's write it. What's this probability? Well, we have to first pick, so this equals to, we have to first pick I elements from here to be the common elements with A, right? We know that the number of common elements is strictly bigger than that, so we pick I, which is strictly bigger than alpha n, up to n/2 to be the common element with A. So then this is the number of ways to choose common elements with A. And then we have to choose from complements of the first n² elements, the remaining elements, to make it up to set A. So you have to choose n², wait, n², something strange with my notes. It should be A is a half set. In the remaining, we pick 1/2 minus I, no? Why did I write n minus I? Give me a second. I think this is correct. Okay, so this is the total number of ways to pick A. Number of ways to pick a n/2 set. Satisfying this. Okay, now A, we have to pick out of these good sets. So you have to multiply by n choose n over 2 inverse. That's the total number of half sets. You need to hit one of these good ones. Okay, let me double check. You first choose n half, some common elements, I of them. And we know I is strictly bigger than alpha n. And in the remaining n over 2, you need to choose n over 2 minus I, no? So they sum up to n over 2 size. That's a half sets. Yeah, I think so. Yeah. Now, estimate this. This, I think, is calculation. This is where we use alpha is bigger than, strictly bigger than 1/4. When alpha is strictly bigger than 1/4, what we use is this fact that the sum of binomial coefficients I from 0 to something strictly less than half minus epsilon n, okay, is less than equal to 2 to the n minus epsilon squared n. This is called concentration of measure. Okay. Using this fact, we can get that when alpha is strictly bigger than 1/4, if you look at here, forget this term for a moment, you can do the calculation. This is like summing up the, okay, if you forget about this guy, this is summing over all terms that's slightly less than half, up to half of the hypercube, okay? Which is like this here. Replace n by n over 2. We will get that this is strictly exponentially smaller than this guy. So we have this term is, this is calculation. I will leave it for you. Less than 2 to the negative some constant times n. Okay. Calculation. Now, if this is less than 2 to the negative cn, what we do now is we randomly pick these half sets, A1, A2 to AN. Now, pick independently at random n over 2 sets, A1, A2 to the top to AN. We're going to estimate the expected number of pairs where their intersection is bad, is too large. Let x be the random variable counting the number of pairs AI, AJ, such that AI intersect AJ, this is the bad event, larger than alpha n. Okay, we've estimated the probability before, so expectation is easy by linearity of expectation. The expected value of x equals to the probability, let's call this little p, okay, equals to little p. This is linearity of expectation. Times capital N choose 2. We have capital N choose 2 many pairs. So this is at most, as we've calculated, 2 to the negative Cn times n choose 2. Let's say n squared over 2. Okay. Now, here's how we use it. If we choose n to be, let's say, 2 to the negative Cn over 3, then this is satisfied, right? N, what is n squared? N squared is this times 2, which is strictly less than that. So choose n so that this is strictly less than 1. Then what's the first moment we've seen before? If you have a random variable, then with positive probability, where is it? Let's use this one. X is, and most expectation has positive probability, right? And as probably recall X, what is it? Smaller than equal to expectation, right? We have with positive probability, the number of bad pairs, which is X, is at most expectation, which is less than 1. Then my expectation must less than 1 is not enough. Huh? Oh, this one is enough. But X takes integer value, right? As X takes integer value, we have that X is 0 with probability. That means when you choose this many AI, positive probability, the resulting capital N sets, they are pairwise far apart. Any question? This part, I skip some calculation, but this is just pure calculation. I'll leave it for you to fill in. The idea is very simple. You just randomly pick sets, estimate the probability that the overlap is too large, the bad events, okay? Then you randomly pick n sets, you estimate the expected number of bad pairs. Because the bad event happens with very low probability, so we can set a large trials n so that the expected number of bad pairs still strictly less than 1. Since x takes integer value, when x is less than 1, strictly less than 1, that means x must be 0, number of bad pairs. Okay. Second application is about the existence of large sum-free sets in the sets of natural numbers. So let's see sum-free sets. Definition. Sum-free set means you don't have solution. Very simple definition. No a set of integers is sum-free. Let's say S is sum-free if it has no solution to the equation x plus y equal to z. Okay. In other words, different way of saying it is S plus S, the sum set, which this just means A plus B, where A, B, they are elements of S, all right? This just means S plus S and the set S itself has no intersection. That's another way of looking at it. Okay. Some simple example. Let's say if S is the first n integer, sum free sets, the example is you take the odds, 1, 3, 5, 7, two odds numbers sum up to an even number. So no solution to x plus y equals z. Or you take S to be the second half of interval. Okay, let's just take odd because this does not align with my definition. All right. Good. So the theorem we're going to see theorem. For any set of natural numbers, let's call it A1, A2, AN of natural numbers. We must be able to find a subset of it that's sum-free and is large. There exists a sum-free subset S in A that's large with the size of S strictly bigger than size of A, which is n over 3. Okay. We're going to prove it by first moment. So what do we need to do? We need to show that no matter how we're given a set of n natural numbers, A1 to AN, we have to pick some elements from A. We can find more than 1/3 of it so that this subset has no solution to x plus y equal to z. Okay. One remark before I prove this is that this 1/3 is best possible. This is a deep theorem, a very involved construction that's only proved about 10 years ago. So constant 1/3 optimal. This is a construction about 10 years ago by Eberhard, Green, and Manners. So what they prove is that there exists a set of natural numbers in which there's no sum-free sets of size larger than 1/3 plus epsilon fraction. So coming back to this, the proof of this is short but clever. So we're going to prove it by first moment. Basically, we're going to imagine A living in a cyclic group, Zn, Zp, P is some large prime number. And then we're going to consider random dilation of A. And we will show that this random dilation of A will have in expectation hitting the middle 1/3 interval the right number of times. And the middle 1/3 of interval is sum-free. And that will yield us a random subset of A that's sum-free with expectation of size 1/3 times size of A. That's the idea. Okay. So the idea is to consider A leaving Zp, Z mod Pz, a random dilation of A in Zp and apply first moment. Any questions so far about the statement we're going to prove? Okay, so let's prove this. So first, let's take P, a prime that's larger than any of the elements in A. Okay? Take P, take a prime P larger than the maximum elements of A. Okay? Larger than any of the AI. Now we can imagine A living in ZP. Oh, I'm actually going to take P of a particular form. Let's say it's 2 mod 3. Take a prime P that's 3k plus 2 of this form, which is strictly bigger than any of the elements in A. This is doable, basic number theory fact. Okay. Now the first observation is that in the integers mod P, basic fact, in ZP, let's consider the middle one-third into the middle one-third arc. So this is ZP. Okay, 0, 1, 2. This is P minus 1, P minus 2, which equals to what? 3k plus 1, right? 3k. Now you consider the middle one-third interval, which goes from k plus 1 to 2k plus 1. This is roughly middle one-third. This interval is sum free. In ZP, the interval, let's call it I, k plus 1, all the way to 2k plus 1 is sum free subsets of ZP. And here, sum free means even mod P, okay? Even taking modular P. This is easy to check. Now we consider random dilation of A. Random dilation means you multiply by a random element. So let X be a random element in ZP, but which is non-zero. Maybe I should write it like this. Non-zero ZP, right? And this is the non-zero element. You can think of it like this. Okay. And you consider A times X. Now consider the random dilation A time. How do I write it? A times X. Do I write AX? Is it the standard notation? Maybe let me know. Let's just call it set called D. D means random dilation X times AI, where X times A. Yeah. Okay, so A is A1 to AN multiplied by X, random dilation. Now, one basic fact about the cyclic group of prime order is that for any fixed element, for any fixed element of the group in ZP, if you multiply by X, ranging over non-zero elements, you're gonna take all values also in ZP star. Okay. Note that for any element, let's call it A in ZP. Wait. You have to take non-zero ones, right? Give me a second. Okay. For any non-zero elements in ZP star, as X ranges over ZP star, X times A ranges over ZP star. This is basic fact. And what does that imply? We know that each AI is non-zero because we take P to be much larger than A. So A elements in A never wrap around ZP. It's non-zero. This applies to all elements of A, applies to all AI. This implies that as X is uniformly random taken in over ZP star, the probability that X times A lies in this middle interval, this sum-free middle interval, X times A is also uniformly distributed, right? Maybe I should write like this. As X is uniformly distributed, we have X times A is also uniformly distributed. This implies that X times A lies in this interval, probability I over P, right? Which equals to P minus 1, sorry. We are doing everything in ZP star. So this equals to the size of C, the size of I. This set is of size K plus 1. K plus 1 over P is 3K plus 2, so it's 3K plus 1. This is strictly bigger than 1/3. Okay? Strictly bigger than 1/3. Then we can compute the expected number this applies to every element here, AI. We can then compute the expected number of elements in this random dilation overlapping with I. So this implies that expected size of D intercept I equals to linearity of expectation the size of D times this strictly bigger. Let's call this little p. Oh, no, I use p for the prime. Let's call this p0 times p0, which is strictly bigger than 1/3 times D. But the size of D is the same as size of A, right? So equals to size of D is same as size of A. Yeah, that's correct. Even in modulo P. So this is bigger than A is the size, which is n over 3. Good. So what does that mean? That means there exists one dilation. This is our random variable x now. Okay. So imagine this is our random variable x. By first moment, we have there exists with positive probability x, so let me write it out, x bigger than ex with positive probability. What does this mean? This means the same as there exists an outcome of D of this x, which is random dilation D. Exists the outcome of D such that D intercept I size is strictly bigger than n over 3. Okay. Okay. Let's call this set. What does this set look like? For this outcome of D intercept I, let's call it, it looks like XAI. 1, XAI 2 to XAI, let's say M, right? This is how it look like. D is a dilation by X for some X. This is sum free. It actually implies AI1 to AIM is sum free as well. Because if XAI plus XAJ equals to XAK, oh, why use K? AL mod P. This is the reason, okay? If this is not sum free, that means you have some AI plus AJ equal to AL. But then multiplied by X, again, they are the same. Then mod P, of course, they are the same. This will imply this D intercept I is not sum free in ZP. And that's it. This is the set of size the same as D intercept I. We finished the proof. Okay. Any question? Okay, let's talk about next. This is first moment. Okay. Now I want to talk about the next is another important inequality involving first moment, Markov inequality. If we have a random variable taking non-negative values, taking non-negative, let's say, integer values, then we have the probability, which is often the case. We consider some discrete random variable counting something, the cardinality of something. So it's a non-negative integer value. Then the probability that x is bigger than t, some threshold, is at most its expectation over t. In particular, as the expectation of x tends to 0, the probability that x, this is a consequence, equal to 0 tends to 1. Okay? If expectation of x goes to 0, then you can take arbitrarily small t, this still goes to 0, right? So probability equal to 0 tends to 1. This has lots of applications. Well, first of all, if you want to prove some bad event never happens, you can let x to be the random variable counting the number of occurrence of bad events, right? So you want to prove that always good event happens. So you want to prove x equal to 0 with probability tending to 1. All you need to do is to estimate its expectation and show that it tends to 0 with some with some parameter n, which is like with respect to some parameter n. Okay, here's a proof first. The proof is simple. Let's just write down what's the expectation of x. Expectation of a discrete random variable x equals to, we know it takes non-negative integer value. So it takes value 0, 1, 2, 3, 4, k at least 0. Expectation equals to k times the probability that x takes value k. Okay, that's simple. Now let's lower bound it, which is at least, when k is at least t, let's just look at when k is at least t. Then in this term, we replace k by this lower bound t times the probability that x equal to t. Now t is a constant. We can take it out. What's inside? This is the probability that x is at least t. So this equals to okay, rearranging things, we get Markov inequality. All right. This is also first moment. Let's see how we can use Markov inequality. This is a classical application worth mentioning. The existence, a result of Erdős back in the 40s or 60s, the existence of graph with arbitrarily large girth and arbitrarily large chromatic number. So application by Erdős, existence, so graphs with arbitrarily large chromatic number and girth. G. This girth means the length of the shortest cycle in the graph. Okay. Why is the existence of such graph somewhat counterintuitive, surprising? Well, large girth, if you don't have short cycle, intuitively the graph is sparse. And when it's sparse, it's easier to color it, properly color it. So these two are two contradicting property, right? Going against each other. Usually large girth means sparse. Sparse means easier to color, which means small chromatic number. So these two are going against each other. Okay? Two properties against each other. So finding a graph having both these two properties somewhat surprising. The idea, well, now you know we're talking about probabilistic method. We're going to construct such graph in a random way. And we're going to use this first moment, Markov inequality. And here's the idea. We're going to consider a random graph. This is the Erdős-Rényi random graph, which is nothing but you have m vertices, and we put an edge between two vertices with probability p, or some p to be determined. And every pair form an edge with probability p independent of each other, one another. Okay? So the idea is consider random graph on m vertices. Okay. Now with probability p forming an edge for each pair independent of others. Now when p is, there's two things we need to keep track of. When p is large, we want to show chi is large, right? Independence, chromatic number is large. We're gonna prove that independence number is small. When p is large, the idea is that non-meaning how do I phrase it? Non-meaning large, right? Non-meaning independent sets. Non-meaning large independent sets survive. Okay. With large probability, likely, how do I say? Like, if I phrase in a positive way, yeah, whatever, it's all equivalent. If P is large, what I mean is you have a large independent set, I, and the probability that I survive, I form an independent set is what? I choose 2, that's the number of pairs in these sets, okay? And they all, none of the pairs can form an edge. Each pair form an edge with the probability P. So not forming a pair of edge is 1 minus P. 1 minus P raised to this power. You don't want any of the pairs forming an edge. So this is the probability that a large set becomes an independent set. And as you imagine, when P is large, 1 minus p is small. So this whole thing is small. So no large set stays independent. Right. Okay, which means when p is large, likely the independence number is small. The independence number of G, this is random set G, is small. Then it implies chi of G is at least n over alpha G, which is large. Okay. On the other hand, if P is small, then we can estimate that the number of short cycles is small in expectation. Okay, then we can, this is another trick in first moment, we can then delete, we can destroy these short cycles by removing a vertex from each short cycle. Then the resulting graph will have no short cycle, in other words, large girth. Then alteration to get high girth subgraph. Okay, let's see the details. So we have to pick P just at the sweet spot so that it's large enough to have large chromatic number and small enough to have few short cycle. We have to satisfy both. Let P, let's pick, let's say G is the girth we want to hit. So let P to be with n to the 1 over G minus 1, where G is the girth we want to maintain. Okay, and consider GMP. This means this random graph with pairs forming an edge with probability P. Now let's first estimate the number of short cycles. The number of cycles of length L, the number of L cycles is at most, first of all, of all L cycles on M vertices possible, is n to the L over 2L. Very simple one, right? You pick n to the L, you pick L sets. This just means you pick L vertices of the cycle, and you can order it left to right. Okay, this is the overcounting factor. All right. Now each such cycle survive in GMP with probability what? P to the L, because this cycle has L edges. This implies the expected, let X be the random variable, which is the number of L cycles in, let's call this guy G, in G, then expected value of X, which is at most the total number, linearity of expectation, is at most sum of L has to be a triangle, at least 3, up to G minus 1. We don't want any cycle length strictly less than the girth. Then n to the L over 2L times P to the L. Okay, this is the probability expected number. This you can compute some computation, is strictly less than the girth times n to the 1 minus 1 over the girth. Okay. Now we can use Markov. Recall what is Markov? Then by Markov, we have the probability that x is bigger than t. I take t to be n over 2, let's say, is at most expectation of x over n over 2. But what is this? This is something strictly less than 1, right? It's sublinear. G is fixed. This is fixed. Okay, that means this guy tends to 0. Okay, that means when n is sufficiently large, this guy is going to eventually be smaller than, let's say, 1/2, for example, as n tends to infinity. So for large n, large enough n, we have the probability of x at least n over 2 is strictly less than 1/2, let's say. Good. Now, what does that mean? That means we can, with large probability, x is going to be strictly less than n over 2. Number of short cycle. We remove vertex from each short cycle, we're going to have at least half of the vertices remained. These half of vertices induce a subgraph with large girth. All we need to prove now is that its independence number is small in expectation. So use this inequality that chi is at least n over the independence number. We prove that chromatic number is large. So let's say k is the chromatic number. We want to use k is, let's say we want to prove chi is at least k. That's the lower bound. We want to k is the lower bound. Do I want to write this? Okay, let's estimate independence number. So for the natural number R, the probability that independence number of the graph G is at least R. What's this? This is at most. Independence number at least R means there exists R set that remains independent set under this model. In linearity of expectation, oh no, this is union bound. For each fixed R set, the probability that it forms an independent set, as I mentioned, is 1 minus p to the power r choose 2. This is for a fixed R set being independent. The probability that a fixed R set being independent, this is union bound. Okay, now this is less than what? This is less than, use this estimate, n over r is less than en over r to the power r. Okay. If you use this estimate, you will get that this is less than n times e to the negative p r minus 1 over 2, whole thing raised to power r. So what we want is we want this probability also tends to 0. Okay, we want this low probability independence number is large. You just need this to tends to infinity. No, wait. To be strictly less than 1, right? If this is strictly less than 1, this guy will be less than 1, goes to 0 when r grows. So you can just take these to be roughly reciprocal of n. You can take, for example, r equals to, let's say 5 log n over p. I believe it works. Okay. So Rp is what? Rp is roughly log n. So e to the log n is like n to some power. So this whole thing is like n to some power. Tends to 0, raised to power also tends to 0. This implies that for large n, implies for large n, let's get some estimate on this number. What is P? P, we take it to be this number, n to the 1 over g minus 1. So this equals to 5 n to the 1 minus 1 over g times log n. Okay? This is less than n over k for any fixed k when n is large enough. Let's say n over 2k. Okay. So that means, again, when n is large enough, this probability will be less than 1/2. Thus, when n is large enough, the probability that alpha of g is bigger than n over 2k, bigger than r, right? Which is bigger than this is even bigger than that, has probability strictly less than 1/2. Okay, so when n is large enough, we have this. We also have this. Remember, both of which happens with probability strictly less than half. That means with positive probability, we have both of the events that x is strictly less than 1/2. This is the number of short cycles. Short means strictly less than g. And alpha of g is at most n over 2k. Okay, we have both of these. Now, as I said, delete a vertex from each copy of a cycle of length strictly less than g. You get the induced subgraph G prime, okay, number of vertices of G prime is is at least n minus x, which is at least n over 2 vertices remained, right? What is the independence number never increase? Alpha of G prime is at most alpha of G. When you zoom into a subset in the sum graph, independence number never increase, n over 2k. This implies chi of G prime is at least number of vertices in G prime over alpha of G prime, which is at least k. Okay, that's it. We have a subgraph of chromatic number at least k and girth at least g. Any question? Um, so next time I will prove this fact here, which I skipped. Earlier, I mentioned this concentration of measure that in the hypercube, if you take the weight somewhere below half of the cube, this weight is negligible. That's what this means. Okay. In other words, in the hypercube, most of the weight is concentrated around mid layers. This is used here in this computation. Next time we will prove this. It's general phenomenon of concentration of measure. And next time, what else we will see? We will see one more application of this first moment methods. The proof of similarity-Trotter theorem, a very classical theorem on a number of incidents of points and lines in the plane. Okay, this will be on Thursday. Any question for today's lecture? All right, if there's no question, I will see you guys on Thursday.